Hello students, very good afternoon to all of you. So today we will discuss the PYQ of the engineering services and gate pertaining to bending stresses and shear stress in beam. This is also one of the important chapter of strength of material. So we will discuss the PYQ today, and let us start one by one. This is a engineering services 2017 question. The span of a cantilever beam The span of a cantilever beam is 2 meter. The cross section of the beam is a hollow squares with external sides 100 and its moment of inertia is this much. The safe bending stresses for the beam material is 100 Newton per mm square. The safe concentrated load at the free end would be how much? So this is a cantilever beam. Its span is 2 meter and there is a point load at the free end. Let it be W. So this W is to be determined and its cross section is this one. This is a hollow cross section and its external side is 100 mm. So this is the cross section. Its moment of inertia is 4 into 10 raised to the power 5 mm raised to the power 4. The safe bending stress is F is equal to 100 Newton per mm square. So in this case, the cantilever will deflect like this, and the maximum bend moment will be developed at the free end, and it will be like this. It will be hogging, and moment at this end, at the fixed end, where the bending moment is maximum, it will be W into 2. It will be 2W. Let the W is in kilonewton. So it will be 2W kilonewton meter. So this is the bending moment M, which is maximum here, and this M is equal to F into section modulus, and section modulus is equal to I upon Y. So now if I put the value here in these equations, then M is equal to Fz and M is equal to 2W. It is in kilonewton meter. If I multiplied it by 10 raised to the power 6, it will be in Newton mm. This M is equal to F. F is 100 into moment of inertia. This 4 into 10 raised to the power 5 upon Y. Y is where the stress will be maximum. So it will be like this: tensile stress on the top fiber and compressive on the bottom. So from the neutral axis and the top fiber, the distance is 50 mm. This is the neutral axis, and this Y is equal to half of this 100 mm. So it is 50. So this I upon Y means this is 50. Now so W will be it will be 2 upon 5 kilonewton. So 2 upon 5 kilonewton means 2 upon 5 kilonewton. If I multiply it by 1000, it will be in Newton. So it will be 400 Newton. 400 Newton means this one. So this D is the right answer. Second question, a homogeneous prismatic simply supported beam, this is a beam and span is L, is subjected to a point load F here. The load can be placed anywhere along the span of the beam. The very maximum flexure stresses developed in the beam is how much? So maximum flexure stresses means maximum bending stresses. And maximum bending stresses will be developed when the bending moment is maximum, and bending moment will be maximum when this load F is applied at the center. So in this case, maximum flexure stresses will be developed. So load position is at the center. So F is here. Now I have to know the bending stresses. So it will be like this: compressive on the top and tensile on the bottom. So it will deflect like this. So here it is compressive, and this is, and this extreme fiber, this is FC, FT. This F is equal to M upon Z. And what is the bending moment? The bending moment will be maximum at the center. If I draw a bending moment, it will be like this. Reaction will be half F by 2, F by 2. Then bending moment will be FL upon 4. So it will be maximum at the center. So M is equal to FL upon 4. So if I put the value of M here, it will be FL upon 4 divided by Z. Z is section modulus. So section modulus of this along this axis is equal to BD square upon 6. This is BD square upon 6 is the section modulus Z. So I is equal to BD cube upon 12, and section modulus is I upon Y. It will be BD square upon 6. So this will give F. So now this will be, so it will be 3 upon 2 FL upon BD square. This will give F. So 3 by 2 FL upon BD square. So this is the right option. On the next question, a steel wire of 20 mm diameter is bent into a circular shape of 10 meter radius. If E is the modulus of elasticity is this much, then the maximum tensile stress induced in the wire is nearly this much. So this is my steel wire, and after bending, it will bend like this, suppose. So this is a circular arc. So it will be R, radius of curvature. This is R, and its cross section is like this. This is a 20 mm dia. The cross section of the bar is like this. This is a 20 mm dia. It is bent in this way. Circular arc shape of 10 meter radius. This R is equal to 10 meter. And modulus of elasticity is this much. E is 2 into 10 raised to the power 6 kg per centimeter square. So now I have to find the maximum tensile stresses induced in the wire. So maximum tensile stresses will be developed on the top fiber. It will be tensile here, and bottom will be compressive. So formula is, what is the bending formula? M upon I is equal to F upon Y is equal to E upon R. So this F is required to be determined. So F will be Y into E upon R. So F is equal to, what is Y? Y is from the neutral axis. So its neutral axis will be this. So this will be my Y. Distance from the neutral axis to the top fiber, it will be half of this 20. So it will be 10 mm. 10 mm means 1 centimeter. So if I calculate in centimeter, so Y is equal to, this Y is equal to 1 centimeter into E. Young modulus of elasticity, it is 2 into 10 raised to power 6 kilogram per centimeter square, and R. R is 10 meter here. This is the radius of curvature, which is 10. So it will be, yes, this R is in 10 meter. So I have to convert it into centimeter. Centimeter means I will multiplied by 100, it will be in centimeter. So now F will be 2 into 10 raised to power 3 kilogram per centimeter square. Means this one is the right answer. In the case of a rectangular beam subjected to a transverse shearing force, the ratio of the maximum shear stress to average shear stress is 1.5. As I have explained in my lecture, in case of rectangular section, stress distribution will be like this. So it will be maximum at the neutral axis, and on the top it is 0. And this maximum Q max is equal to 1.5 times of Q average. Q average is 1.5 into shear force divided by the cross section area. Suppose this is B, this is BD. So this is 1.5 times of the average. So this one is the right option. Which one of the following statements specifies shear flow? Shear flow is basically, what is the formula of shear stress? Is equal to S A Y bar upon IB. This is the shear stress. So this S is the shear force. Suppose this is the rectangular sections, and I have to find the shear stress at this level. Now, for finding the shear stress at this level, first I must know this value of the S. S is the shear force, and A is the area above the layer, above this layer, where Q is to be determined. So this area into, from the neutral axis, this distance is Y bar. From the centroid of this section, this area to the neutral axis, this distance is Y bar divided by moment of inertia of the whole section about neutral axis into this B. B is this width. So this is the formula for shear stress. Now, if I multiplied it by B, so it will give Q is equal to S A Y bar upon I. So this will give shear flow. This is a formula for shear flow. It will give shear force per unit length. So it will give per unit length. This Q is in Newton per mm square. If I multiplied by B is the mm, so it will be Newton per mm. So this will be shear flow. Shear flow is shear intensity per mm length. So this is the formula for shear flow. So flow of the shear force along the beam, it is the product of the shear stress at any level and the corresponding width of the section. This one is the shear stress, and so this is Q dash. This is the shear stress into B, width of the sections. So this one is the right option. Unbalanced force on any one side of a given section divided by the area of the section. The deformation at any level due to sudden variation in shear stress. So this is wrong. So right option is this one. It is the product of the shear stress at any level and the corresponding width of the section. This one. So this is the right option. A beam of triangular cross section is subjected to a shear force of 50 kN. The base width of the section is 250 mm and the height is 200 mm. The beam is placed with its base horizontal. The shear stress at a neutral axis will be how much? So my beam cross section is like this. Is it triangular shape? Its base width is 250 mm and it is 200 mm is the height. So beam is placed with its base horizontal. The shear stress at the neutral axis. Its neutral axis will be here. So it will be 1/3 of this one. So it is 200 divided by 3 mm and it will be 2s/3 means 400 by 3 mm. So this is the neutral axis position. Now the value of the shear force S is equal to 50 kN. So shear stress intensity at this level means I have to calculate it from the equation. Q is equal to SA y bar upon IB. This is the formula where Q is equal to S. S is the shear force which is 50 kN. Kilonewton means 10 raised to the power, it is in Newton, into AY. AY means area about this layer. The area of this will be the base width. The base width will be this base width. I can calculate from two similar triangle. So this side divided by this is equal to this side its height which is 400 by 3 divided by its total height which is 200. So this will be 400 by 3 into 250 upon 200. So it will be 2. So it will be 250. It will be 500 by 3. So it is 500 by 3 mm from here to here. Now in this formula Q is equal to SAY. S is this much. Area of this will be this side which is 500 by 3 is the base into this height. This is 400 by 3 into 1 by 2. This is the area of this portion into its distance from the centroid of this area, and this is the neutral axis. So this distance will be 1 by 3 of this one, 1 by 3 of this one, total height. So this SA y bar upon moment of inertia. So moment of inertia of the triangle about its centroid will be B h cube upon 36. So this is the formula of moment of inertia of a triangular portion about its neutral axis is equal to B h cube upon 36. This is the value of the I. So I is equal to this moment of inertia of the whole portion. This will be B into H is equal to 200 upon 36. So this is the I into B. B is the width. This is 500 by 3. So with this we will get the value of the Q. So Q will be 50 into 10 is power 3 into 500 by 3 into 400 by 3 into 1 by 2 into 1 by 3 into 400 by 3, and anyway we can calculate this. This will calculate, and the calculation part you people can do. I will not consume the time. So from this, the value of the Q, that will be 8 by 3. It will be 2.6 N, 2.7 Newton per mm square will be the answer. Now a timber beam of 100 meter wide and 150 mm deep supports a UDL over a span of 2 meter. So it's like this. This is 100 mm. This is 150 mm. This is timber beam, and it supports a UDL. Span is 2 meter. This span is W per unit length. Two meter. So in this case, the bending stress limit is 28 Newton per mm square, and Q is stresses. Safe stresses are not to exceed 20 MPa in bending and 2 MPa in shear. I have to calculate the maximum load that the beam can support. The maximum load that the beam can support means W. This W is required to be known. So this is 2 MPa is. Now as we know, F is equal to m upon I is equal to f upon y is equal to E upon R. So this f is equal to m upon I into y, and this is mz. So f is equal to mz, and the value of f is 28 is equal to bending moment. So its bending moment will be maximum here. So it will be W into L square by 8. This will be in kilonewton. Suppose this is kilonewton meter, so it will be kilonewton meter. So m is equal to W into 2 square by 8 in kilonewton meter. I will multiply it by this. This is m divided by z. Z is section modulus. Section modulus of this is equal to BD square by 6. This is section modulus. So this W will be so it will be W is equal to 7 into 3. It is 21. So 21 kilonewton per meter is the W from bending equation. Now if I calculate it from shear formula, this Q is equal to SAY upon I bar IB. Shear force will be how much? So total load is W into 2, and W into 2 is the total load divided by 2. So reaction here will be W kilonewton. W kilonewton is the reaction here. This is the shear force. So this shear force is W, which is in kilonewton. Means I will multiply it by 10 raised to the power 3. So this will be in Newton, and my shear stress will be maximum here. Maximum will be at the neutral axis. So area of this portion, bending stress will be like this, the shear stress. So area of this portion, this will be 100 into 75. So this is half of this into distance from its center to the neutral axis. This is 37.5 divided by moment of inertia. This is BD cube upon 12 into this base. This is 100. So this 12 I can take here, and this will be no. So W will be this W will be 150 upon 7.5. So it will be 20. So the maximum load that can be support is the least of the two in bending and shear. So from bending criteria, it is 2.7. Oh, this is, I think, the next, this one is the next question. So from shear criteria it is 20, and from bending it is 21. So the lesser of the two is 20 kilonewton. So the safe load is 20 kilonewton per meter. It means this B is the right option. Now the maximum shear stress across a circular section is 4/3 of the average. Yes, in case of circular section, shear stress is like this. It will be maximum at the neutral axis, and this Q max, this is Q max, this is 4/3 times of Q average, or I can say 1.33 times of Q average. In case of rectangular section, it is 3/2. In case of rectangular, it is 1.5 times of Q average. In case of circular, it is 1.33 times of Q average. 1.33 means 4/3. So this is the right option. A punch of 20 mm diameter is used to punch a hole in 8 mm thick plate. If the force required to create a hole is 110 kilonewton, the average shear stress in the plate will be, so this is the plate and this is the hole. This is the plane. If I draw the cross section, it will be like this. So this is my hole. Now the average shear stress in the plate will be how much? So this will be, this force required to create a hole is shear force is 110 kilonewton. So this is 110 kilonewton is the shear force, and it will be resisted by here like this. This shear stress is like this, and it will be on the periphery like this. So perimeter of this will be pi d into this thickness. So pi d is the perimeter into this thickness. So this will be the surface area where shear stress will act, and this will be equal to this one. So shear stress will be this shear force divided by this shear circumference area. So this Q will be 1000 in multiplied by 10 to the power is in Newton upon pi d means 22 upon 7 into d. D is the die of the hole. The die is 20 mm into its thickness. Thickness is 8 mm. This thickness is 8 mm T. This is pi d T. So now it will be it will be 1000 into 7 upon 4 into 8. So this will be 250 and so it will be approximately 220. So this 220 is the right option. A circular beam of 100 mm diameter is subjected to a shear force of 30 kilonewton. The shear force is 30 kilonewton. The maximum shear stress will be how much? So in case of circular section, the maximum shear stress, this is maximum at the neutral axis, and this Q max is equal to 1.33 times, or I can say 4 by 3 times of Q average. And what is the Q average? Q average will be this shear force. This is in Newton divided by area of a cross section. So area of cross section will be This is 100 mm dia, so it will be pi d square by 4. So this will be the formula. So Q max is equal to 4 by 3 so it will be 56 upon 11. It will be 5.1 MPa. It means this one is the right option. A floor has to carry a load of 12 kilonewton per meter square. The floor is supported on rectangular joist, each 100 mm wide and 300 mm deep and 5 meter long. So joist is like this. So this is slab. So these are my joist, and this center to center, this distance, this is a floor, and it is 12 kilonewton per meter square. Now the cross section of this joist is, it is 100 mm and 300 mm and 5 meter long. Its length is 5 meter long, like this. So this is 5 meter long. If the maximum stress in the joist should not exceed 8 mm meganewton, this is bending stress. 8 meganewton means 8 into 10 raised to the power 3 kilonewton per meter square. If I convert it in kilonewton, it will be this. So this is the M. Now there will be a load of the floor which will act, and this W will be how much? So the load on the joist is basically half of this portion. So if this spacing is, how much is the spacing? So this load is 12 kilonewton per meter square. The floor is supported on rectangular joist, each 100 mm wide, and this is if the maximum stress in the joist, the center to center distance of the joist will be this one. So if suppose the center, this distance is S, this spacing is S. So load on this will be half of this. So it will be half of this much. So half of this means half on this side and half on this side. This much load will act on a joist. So this S into 1 meter. 1 meter length is along the length 1 meter into S into 1. So this will give W per unit length. So it will be 12 kilonewton is the intensity. So 12 multiplied by this S. This S is, this is also S into 1 meter length. So this will be 12 into S into 1. So it means this is 12 S kilonewton per meter. So this is the intensity. Now bending moment will be WL square by 8. So this M is equal to intensity is 12S into L square divided by 8. This is bending moment. and m is equal to fz. The bending moment is 12 into s into L square by 8. So this is in kilonewton meter. So this is in kilonewton meter. M is equal to Fz. My stress is in kilonewton meter. F into Z. Z is section modulus. And section modulus will be how much? It will be, since this is in kilonewton per meter square, so if I multiplied it by 10 raised to the power 3, this will be kilonewton mm. And if I divide this by 1000 square, it will be kilonewton per mm square. So this is F into Z. Z is section modulus. It will be B into D square by 6. With this, I can calculate the S. So S will be 8 into 10 raised to the power 3 into 1000 into 300 into 300 into this 8 into 10 raised to the power 3 divided by this 12 into this into 1000 square into 6. So oh, this will be no. So this is 50 into 8, 400 into this one divided by this is oh no, this is 400 into by so this will be, I think this will be, it will be 0.32 meter, means 320 mm. So this one is the right option. Calculation part you people can do. A simply supported wooden beam of 100 mm wide and 200 mm deep. So this is 100 mm width and depth is 250 mm. It is 3 meter long. Carrying a UDL of 40 kN per meter. The maximum shear stress will be how much? Maximum shear stress means, as we know, maximum stress in rectangular it will be 1.5 times of Q average. And what is Q average? This is shear force divided by the cross section area, F upon BD. So what will be the shear force will be maximum here? So it will be 40 into 3 is the total load 120 kilonewton. So reaction here will be 60 kilonewton and 60 kilonewton. So my shear force here is 60 kilonewton. It will be like this: 60 kilonewton, 60 kilonewton. This is the shear force. So maximum shear force is this 60 kilonewton. So this 60 kilonewton means this much Newton divided by its cross section area. This is 100 into 250. So this will give Q average, F upon BD. This Q average, when I multiplied by 1.5, it will give Q max. So this is Q average and multiplied by 1.5 Q. So this will be so it will be 18 upon 5 and 18 upon 5 will be 3.6 Newton per mm square, means MPa. So this 3.6, this one is the right option. A wooden floor is required to carry a load of this one and is to be supported by wooden joist of 120 mm and 250 mm. Cover a span of 4 meter. If the bending stress in the wooden joist is not to exceed this, what is the spacing of the joist? This is a similar question as we discussed earlier. So this is the floor, 12 kilonewton per meter square is the intensity, and these are my joist. So this is the spacing. So load on one joist will be this one. So this much load means this 12 into this S spacing into 1 meter length along the length. So this S into 1, this will be the intensity. So 12 S kilonewton per meter, this is the intensity. Now its cross section is this one, and span is 4 meter. So bending stresses in the is not to exceed 8 MPa. So F bending stress is equal to 8 Newton per mm square is given, and this F is equal to M is equal to Fz. So what will the bending moment, maximum bending moment will be here? It will be WL square by 8, means 12S is the intensity into L square divided by 8. This is in kilonewton meter. So this is bending moment M, and this M is equal to 12 into S into L square upon 8 multiplied by 10 raised to the power 6 is Newton mm. M is equal to Fz. F is 8 into section modulus. Section modulus is BD square by 6. This is B D square upon 6. This is section modulus. So means 120 into 250 square divided by 6. This is section modulus. M is equal to Fz. With this equation we can find S. So S will be, this S will be 8 into 120 into 250 into 250, this one into this 8 divided by 6 into this 12, this 4 square into this one. Now so this is 5 upon 12. So 5 upon 12 means this is in 5 upon 12. So it will be 0.4 this will be something like this in meter. When I multiplied by mm, so it will be 417 mm, means this is the right option. A steel plate of 120 mm wide and 220 mm thick is bent into a circular arc of radius 10 meter like this. So this is my circular arc, its radius is 10 meter. This is R, the circular arc, and this steel plate is 120 mm wide and 20 mm thick. So this plate is like this. This is 120 mm is the width and 20 mm is the thickness. What is the maximum stress produced and the bending moment which can produce this stress respectively? Take E is equal to 200 gigapascal, means 2 into 10 to the power 5 megapascal is this one. So I have to know the maximum stress produced and the bending moment which can produce this stress. So first F is required. Bending stress F is equal to how much? F M upon I is equal to F upon Y is equal to E upon R. With this equation F upon Y is equal to E upon R, I can find F. So F will be equal to E upon R into Y. And what is E? 2 into 10 to the power 5 divided by R. R is how much? This is 10 meter into 1000. This is in mm into Y. Y is this one. The plate neutral axis will be here, and the distance of the top fiber from this neutral axis is half of this. This is 20 mm, so it will be 10 mm. So Y is equal to 10 mm. So with this, I can calculate F. So it will be So it will be 200 Newton per mm square, means 200 megapascal. So 200 megapascal is in this option and this option. So means I have to check the bending moment also. So M is equal to, as we know, Fz. This F is equal to M upon I into Y, means Fz. F is the 200. Z is section modulus. Section modulus of this will be BD square by 6. B is 120. D is 20 square upon 6. So this will be 2 into 2. So this will be in Newton mm. When I multiply and divide by 1000, so it will give Newton meter. So this is a Newton meter. So this will be 1600 Newton meter. Means this one is the right option. Which one of the above statements are correct? Consider the following assumption for pure bending theory. The material is heterogeneous. So correct statement means it is not heterogeneous, it is homogeneous. So this one is wrong. The stress is purely longitudinal and local effects near concentrated load will be the stress is purely longitudinal and local effects near concentrated loads will be neglected. So the radius of curvature is large compared with the dimension of the cross sections. Yes, the pure bending like this. Pure bending means my shear bending moment is constant. So it is just like a circular arc. So circular arc means my moment is constant, m is constant. So for a small steep or dx we can consider this one. So this is okay. The stress is purely longitudinal and local effect near the concentrated loads will be neglected. This is also correct. So purely longitudinal means m is constant. So it is not varying, and local effect near concentrated load will be neglected. If suppose this is a concentrated load, its local effect is neglected. So this 2 and 3 is the right option. For a rectangular beam of 4 meter long with 100 mm wide and 200 deep, like this. It carries a shear force of 100 kilonewton. Means shear force S is equal to 100 kilonewton. What is the maximum shear stress, tau max, due to bending of rectangular section? So in case of rectangular, what is the formula for Q max? It is 1.5 times of Q average, means 3/2 of the Q average. And what is Q average? Shear force, this is in Newton, divided by the cross section area. This is 100 into 200. So this will give Q max. Now so it will be 15/2 means 7.5. So this one is the right option. A simply supported steel beam of 8 meter long and subjected to a UDL. This is simply supported beam, 8 meter long. It's carrying a UDL of 10 kilonewton per meter. What is the maximum bending stress of the member at a distance of 50 mm from the neutral axis? From the neutral axis. Maximum bending stress is so in this case bending moment will be M is equal to WL square by 8. So this is in kilonewton, 10 into 8 square upon 8. So this is in kilonewton meter. So the maximum bending moment. And this M is equal to Fz. This will give on the top fiber. This is Y max. So this will give, but I have to find the maximum bending moment stress at 50 mm from the neutral axis. 50 meter from the neutral axis means if this is a rectangular beam, so this is neutral axis, so it will be 50 mm from here. So at this level, what will be the bending stress? So this will be M upon I is equal to F upon Y. So in this case, M is equal to F upon I into Y. And what is M? M is 10 into 8 square by 8 is in kilonewton, means this is Newton mm. This M is equal to F upon Y. Moment of inertia is this much into Y. Y, this Y is the distance from the neutral axis. This distance from the neutral axis at which the stress is to be calculated. So this Y will become this 50 mm. So this will give stress at this level. When I put the value of the Y, this one, so it will give extreme fiber stresses. If I want to know at this point, then y will become this one. So this y is 50 mm. Now F will be 10 into 8 into 8 into 10 raised to the power 6. This is F. Oh, I think it's wrong. F into y upon y. F upon y into y. So F into moment of inertia, this divided by y. So this and this will cancel. This is 8 here. So this will become 80. So this F will be 10 into 8 into this 50. So this will be 4000 Newton per mm square. So this will be the value of the F. Means this one is the right option. A rectangular CS beam of size 300 mm into 500 mm is subject to a shear force of 20 kN. What is the shear stress at 150 mm from above the neutral axis? So section of the beam is like this. This is 300, this is 500, and the value of the shear force is 20 kilonewton. What is the shear stress at 150 mm about the neutral axis? 150 mm above the neutral axis, so its neutral axis will be here. So this will be 250 and 150 mm above the neutral axis means at this layer. So this is 150 mm above the neutral axis means this distance is 100 mm. So at this level, what will be the shear stress? So this shear stress will be like this. So at this level, this shear stress at this level is to be calculated. The formula is Q is equal to SAY bar into upon IB. What is S? S is the shear force, which is 20 kilonewton. This is Newton into AY. AY means area of this portion, which is 100 into, this is 300, this is 100. So this is 100 into 300 into this distance from its centroid to the neutral axis. This is 150 plus half of this will be 200 upon moment of inertia. Moment of inertia will be BD cube upon 12 B D cube upon 12, moment of inertia of the whole beam. So this will be this divided by 12 means BD cube upon 12, this into this B. B is this width. This is 300 mm. This 300. This is also 300 mm. Now this will be 2 into 2, 4 into 4 is 16 divided by this will be 125. So 16 upon 125 will be 0.1 approximately 3. So this one is the right options. A rod of circular section is subjected to a shearing force on a plane perpendicular to its axis. What is the maximum shear stress in terms of shearing force and rod diameter if the rod is used as a beam with free ends and a central concentrated load? Express the free length in terms of diameter for which the maximum shear stress due to shearing force is half the maximum direct stress. So a rod of circular section is subjected to a shearing force on a plane perpendicular to its axis. What is the maximum shear stress in terms of shearing force and rod diameter if the rod is used as a beam with free end and a central concentrated load? This is L and this is W. Now its bending moment will be like this, WL upon 4. So this will be the bending moment and its section is this one. This is dia Suppose dia is capital D, then its section modulus will be, section modulus of the circular section is a pi d4 upon 32. It will be I upon y. So I is pi d4 upon 62 divided by d by 2. So it will be pi d cube upon 32. This is section modulus. So if I calculate its bending stress, it will be F is equal to m upon z. What is m? M is WL by 4 divided by section modulus. It is equal to pi d cube upon 32. So it will be WL by 4 into 32 upon pi d cube. So this will be my, and this will be 8 WL upon pi d cube. So this is F. F is 8 WL upon pi d cube. Now what he says that the shear force is the maximum shearing stress is due to shearing force is half the maximum direct stress. So maximum direct stress is this one. So this is maximum bending moment. M upon Z is this stress. So half of this. So half of this stress means half of this will become the maximum shearing stresses, Q max. And what is Q max? For circular section, Q max is equal to 1.33 times or 4 by 3 of Q average. And what is Q average? Q average will be shear force divided by cross section area. What is shear force? Shear force will be W by 2 here. It is W by 2. So shear force is W by 2 divided by cross section area. Cross section of the circular bar is pi d square by 4. So this will be 4 by 3 times of Q average is W by 2 is the shear force divided by cross section area pi d square upon 4. This will give Q max. This Q max is equal to 1 by time of maximum direct stress. So now from this equation, this is 4, this 4 and 4 will cancel, W and W will cancel, and this will be D. So oh, so it will be so 2 by 3, it will be 2 by 3 is equal to L upon D or capital D you say. So 2 by 3 is equal to L upon D. So 2 by 3 is equal to L upon D, or I can say L is equal to 2 by 3 times of dia. Means this one is the right option. A circular log of timber has diameter d. The ratio of breadth to depth b upon h of the rectangular beam that can be cut from a circular log for the strongest section in bending is this. Suppose this is my circular log. So the maximum rectangular section or square section that can be cut from this will be this one. So now this is the circular log of timber has diameter d. This diameter is d, and the ratio of the breadth to depth of the rectangular beam that can be cut from the circular log. So this is my rectangular beam. If this is d, then this is also equal to d. This is also the center portion of this rectangular will also pass through the center of the circle. So this is dia of the circular log. So if this is d, this is also equal to d. So this is d. Now if you take this one is d, and the breadth of the this is b of the rectangular beam, and this is its height. So this is the height for strongest section in bending. So strongest section in bending means, so when z is maximum, section modulus is maximum, then I can say this is the strongest section. For strongest section in bending, my section modulus should be maximum, z should be maximum. So it means the derivative of section modulus with respect to its width b, that should be equal to 0. So now what is the value of the z here? Section modulus z is equal to this b bh cube square upon 6. So this is section modulus. Now dz upon db is equal to this is height. So this is derivative of this with respect to b. Now z is equal to b upon 6, and what is h? This h will be, this is 90 degree, so d square is equal to h square upon plus b square is equal to d square. So h square is equal to d square minus b square, means this h square is equal to d square minus b square, means it will become 1 upon 6 into bd square minus b cube. This is my z, and dz upon db will be, that should be equal to 0. It means this d square minus 3b square is equal to 0, means d square is equal to 3b square. So it means d is equal to root of 3 into b, and I have to find the ratio of the width to depth, b upon h. So so this is the equation. Now as we know, d square minus b square is equal to h square. So d square minus b square is equal to h square. So if I convert this d into b, then d square is equal to 3b square minus b square is equal to h square. So it will be 2b square is equal to h square, means root of 2b is equal to h. So b upon h is equal to 1 upon root 2, or I can say 1 is to root 2. So this b upon h ratio is equal to this one. So this one is the right option. The maximum shear stress for a beam of circular section is 4 by 3 times. In case of circular section, Q max is equal to 4 by 3 times of Q average, or 1.33 times of Q average. So this is shear force upon area, this is Q average, and 4 by 3 of this is, so this is the right option. Consider a rectangular hollow section having overall width b and overall depth d, and let the width and depth of the symmetrically placed hole b, b and d respectively. Then this section modulus is, so this is b and this is d, this is small b and this is small d. Now section modulus z is equal to I upon y. So moment of inertia about the neutral axis, this is symmetrical neutral axis. So I will be b d cube upon 12 minus b d cube upon 12. So since both having the same centroidal axis, so outer moment of inertia minus inter moment of inertia, this will be I, this divided by half of this. So half of this is d by 2. So it will become 1 by 12 bd cube minus bd cube into 2 upon d. So it will be bd cube minus bd cube upon 6d. It means this one is the right option. A long rectangular wall is 2 meter wide. The maximum wind pressure on the face of the wall is 1.1 kilonewton per meter square, and the specific weight of the machinery is 22 kilonewton per cubic meter. If the length of the wall is 1 meter, the maximum height of the wall show that there is no tension in the base of the wall. So this is my wall. So this is 2.5 meter. Now the wind pressure is like this. It is 1.1 kilonewton per meter square. So its width is 2.5 meter. Now this is grounded, so this end is fixed. The specific weight of the machinery, gamma, is equal to 22 kilonewton per cubic meter, weight of the machinery, self weight. If the length of the wall means like this length is 1 meter. So it is not to the scale, but we can visualize this length is, although it seems longer than 2.5 meter, but we can understand it. So this is 1 meter. So this load is acting on this portion. So if no tension is to be developed, for no tension to be developed, then what will be the height of the wall? Suppose this is H. For no tension to be developed at this end, means my net stress here, that should be equal to 0. Means due to this, its self weight will create a direct compressive stress here. This will be W upon area. Direct stress is equal to W upon area. What is W? Self weight. Self weight will be there. Its volume 2.5 into this height H into this length 1. This will be the volume into 22. This will become weight. So this will be the weight divided by its area. So area means this one, this area. So this area means 2.5 into 1. So this will give that compressive stress. This will give compressive stress here. So this will be 22H. This will be kilonewton per meter square. And this is in kilonewton. So kilonewton per meter square, this is the direct stress. And bending stress, so due to this load, this is just like a cantilever, and this is UDL. So it will deflect like this. So on this face, tensile stresses will develop. This is a vertical cantilever, and compressive stress will develop here. It will be tensile on the, so tensile stresses, these tensile stresses will be equal to my bending moment here divided by Z. This M upon Z will give the bending stress here. What is the value of the Z? value of the Z is, this will be tensile, so it will be minus. So this is 1.1 kilonewton per meter. Suppose if I consider 1 meter length, then it will be 1.1 kilonewton meter. So this will be the intensity. And what will be the bending moment here? In case of cantilever, it will be W L square by 2. That will be maximum at the fixed end. It will be W into L. L is this height. This height. W L square by 2. So this will be the bending stresses here. This is M divided by section modulus. So section modulus means this one. This bending moment will act on this face. So this face is this one. This is 2.5 and this is 1 meter. So this is 1 meter and this is 2.5 meter. So my this moment will act on this face. So in this case my B, that B will be 1 meter, and so it will act on this face. So this is B 1 meter and this is depth 2.5 meter. So this moment will act on this face. So this BD square upon 6 is the section modulus. So B here is this is 1 and D is 2.5 square by 6. So this will be the Z, BD square by 6. So M upon Z is bending stresses. So the net stress, the total stress will be this plus this, that should be equal to 0. Means this should be equal to this one. It means 22H, that should be equal to this one. So this H will become 2 into 10 into 2 into 0.5 into 2.5 divided by 6, means this will be 25. Now so it will be 125 upon 3. 125 upon 3. It will be 41 point something. That will be the value. So 41 point something means 42. So this is the right option. A simply supported beam of span 3 meter. So this is a simply supported beam. Its span is 3 meter and cross section is this one. 120 into 180 mm. So this is the cross section. If the permissible stress in the material of the beam is 10 Newton per mm square, what is the maximum UDL that it can carry? Ignore the moment due to self weight. So this is my UDL, W per unit run. So maximum permissible stress in the material is 10 Newton mm squares. So this is F. F is bending stress, means 10 Newton per mm square. This F is equal to, as we know, M is equal to Fz. So M is equal to how much? This will be WL square by 8, means W into 3 square by 8. This is in kilonewton per meter. So W L square by 8 is in kilonewton meter, multiplied by 10 raised to the power 6. This will be Newton mm. This M is equal to Fz. F is 10 into Z. Z is section modulus about the neutral axis. This is BD square upon 6. BD square upon 6 is the section modulus. So with this I can calculate the W. So W will be 10 into 120 into 180 into 180 into 8 upon 6 into 3 into 3 into 10 raised to the power 6. So O this will be 4 into 18 is equal to 72. 72 into 8. This will be on 100. So it will be 5.76 kilonewton per meter. It means this one is the right option. A cantilever wooden beam is 3 meter long and carries a UDL. This is a cantilever. Its span is 3 meter and it carries a UDL of 4 kilonewton per meter. The cross section of the beam is this one. What is the maximum bending stress for this section? So its bending moment will be like this, WL square by 2. Bending moment will be WL square by 2, 4 into 3 square by 2. It will be maximum here. This is in kilonewton meter. So this is M. M is equal to Fz. So M is 4 into 3 square by 2 is kilonewton meter, multiplied by 10 to the power 6 is Newton mm. This is equal to F is bending stress. This I have to know, into Z. Z is section modulus. Section modulus about the neutral axis will be BD square upon 6. B into D square upon 6. With this I can calculate my F. So this will be 200 into 200, I say. So this and this will cancel. So F is equal to 3 square means into 3. So this will be 27. So 27 Newton per mm square means 27 megapascal. So this one is the right option. So now these are the question of gate. A cantilever beam of 2 meters length with a square section of side length 0.1 meter. So this is 0.1 meter, this is 0.1 meter. The square sections is loaded vertically at the free end. This is W, and this 5 mm is the vertical deflection here. So this is 5 mm vertical deflection here. The beam is made of steel with Young modulus E is equal to 2 into 10 to the power 5 11 Newton per mm Newton per meter square. The maximum bending stress at the fixed end will be how much? So for this, its bending moment will be like this, W into L. So this is L, then it will be, this length is 2 meter, so it will be 2W. So this is M. So first I have to know this W. So this vertical deflection is 5 mm, means vertical deflection at the free end is equal to W L cube upon 3 EI. This is the formula for vertical deflection at the free end. This is equal to 5 mm, means 5 upon 1000 meter. So W L cube upon 3 EI is equal to this much. So it means 5 into 3 EI upon 1000 into 2 raised to the power 3. This is in this E is in so this is kilonewton. So this is the value of the W, and this bending moment is W into 2. This is 2W here. So this F Z is equal to M. So F is M upon Z. And what is M? It is 2W. So F is equal to M is equal to 2W. 2W means 2 times of this. This is M, and this is in kilonewton meter. So this is in kilonewton meter. F divided by I. I will be divided by Z. So Z is equal to I upon Y. So I upon Y is the Z, and Y is equal to half of this. Half of this will be 0.05 meter. So I and I will cancel, and if I put the value of E is equal to this much, so in kilonewton meter it will be 2 into 10 raised to the power 8 kilonewton per meter square. If I put the value of E here, it will be F is equal to 2 into 15 into 2 into 10 raised to the power 8 into 0.05 divided by 1000 into 8. So this will give bending stresses in kilonewton per meter square. So kilonewton per meter square means if I multiplied by 10 raised to the power 3 and divided by 1000 square, so it will be Newton per mm square. So it will be so this will be 150 upon 4, and 150 upon 4 is 37.5, means this one is the right option. A 8 meter long simply supported elastic beam of rectangular cross section is subjected to a UDL. So this is a simply supported beam, 8 meter long, it's carrying a UDL of 10 kilonewton per meter. This section is the maximum principal stress. Maximum principal stress means sigma in MPa up to 2 decimal place at a point located at the extreme compression edge of a cross section. So extreme compression edge will be like this. This is the extreme compression edge. So this will deflect like this. Compression will be on the top fiber. So at this point, my maximum principal stress, how much it will be? At 2 meter from the supports. Means first I have to calculate my F, bending stress at this. So this bending moment at this mx will be m at this point 2 meter from the supports. So this bending moment will be, total load is 10 into, this is 80 is the total. So 40 kilonewton is the reaction. So bending moment at this point, it will be 40 into 2 minus 10 into 2 square by 2. So this will be 80 minus 20. It means 60 kilonewton meter is the bending moment here. It is 60 kilonewton meter at this point. 60 kilonewton meter is the bending moment at this point. So this m upon z is equal to f. So maximum bending stress will be here. So f is equal to m upon z. M is 60 kilonewton meter, means this is in Newton mm divided by z. Z is section modulus. Section modulus of this will be BD square by 6. So it will be 60 into 10 is to the power 6 into 6 upon 100. This will be. Now so it will be 90 Newton per mm square. Now as shear stress here, the shear stress is like this. So where compression is maximum, my shear stress Q is equal to 0. Q is equal to 0 means principal stress, formula of principal stress is, this is F minus plus 0 by 2 plus F minus 0 by 2 whole square plus Q square. This is a formula. So on this face, on the other face, bending stress is 0. This is sigma is equal to F by 2 plus this Q is also 0 here. So this will be F by 2 means F. It means my maximum principal stress here is equal to the maximum bending stress. Maximum bending stress is equal to 90 Newton per mm square. So the answer is 90 megapascal or 90 Newton per mm square. This is the answer. For a given loading on a rectangular plane concrete beam with an overall depth of 500 mm, the compressive strain and tensile strain developed by the extreme fiber are of the same magnitude of this. The curvature in the beam cross section is per meter. Round off 3 decimals, how it will be. So suppose this is a beam. It may be like this. So overall depth is 500 mm and the rectangular plane concrete beam with overall depth of 500. The compressive strain and tensile strain developed at the extreme ends. So its strain diagram will be like this. This is strain. So strain is 2.5 into 10 raised to the power 4. This is strain, and this strain is also equal to this. And as we know, stress upon strain is equal to E. So stress is equal to strain into E. It means if I multiply by this Young modulus, it will give bending stress. So this is my bending stress. As we know, M upon I is equal to F upon Y is equal to E upon R. So with this equation, this curvature means 1 upon r. So 1 upon r is the curvature. This will be equal to F upon EI. And this F is equal to how much? This is 2.5 into 10 raised to the power minus 4 into Young modulus of elasticity divided by EY. E into Y. Y is how much? Y is this distance from the neutral axis to this one. So this is 250 mm. This Y is 250 mm. This E and E will cancel each other. So this will be so it will be 10 raised to the power 4 upon 100. This is in mm. So this is in mm. So this is my 1 upon r per mm. This is per mm. Means when I multiplied by 1000, it will be in meter. So it will be this per meter. Curvature means 1 upon 1000 per meter. So this is the curvature. So answer is 1 upon 1000, or I can say 0.001. This is the answer. The cross section of a built up wooden beam as shown in the figure not drawn to scale is subjected to a vertical shear force of 8 kilonewton. So this is the cross sections. The shear force here is vertical shear force is 8 kilonewton. The wooden beam, so vertical shear force is 8 kilonewton. The beam is symmetrical about the neutral axis shown, and the moment of inertia about the neutral axis is this much. So this is symmetrical about the neutral axis, and its moment of inertia is considering that the nails at the location P, at this location P, these are the nails. Nail at this location are spaced longitudinally along the length of the beam at 60 mm interval. So 60 mm is the spacing. Each of the nail at P will be subjected to a shear force of how much? How much will be the shear force of the nail at this? So this is the cross section of a wooden beam is as shown in the figure. Is subject to a vertical shear force is this one. The beam is symmetrical about the neutral axis, and the moment of inertia is this one. Considering that the nails at the location P are spaced longitudinally along the length of the beam at 60 mm is the spacing. Each of the nail at P will be subject to a shear force of how much it will. So in this case, my shear flow means shear stress formula is this one. So when I multiplied it by B, then it will be SAY bar upon I. So this will be the shear flow, means shear force per unit length, per mm length, SAY bar upon I. Now at this location, if I want to find, then shear force will be shear force is 8 into 10 raised to power 3, this is in Newton, into area. So area of this will be, this is 50 mm. So at this junction, this is 50, this is 50. So this will be, area will be 50, this is 50 into 50 into 2. So this will be the area into Y bar. Y bar will be, this is 200, 400, 200 minus this 50. So this distance is 150. This is SAY bar divided by moment of inertia. This is 1.5 into 10 raised to the power 9. This will give shear flow per unit length. And this will be 4 Newton per mm. Now my spacing of the nails is 60 mm. So it will be 60 mm is the length. Now shear force will be, this is per mm, and for 60 mm it will be 4 into 60. So it will be 240 Newton. So this one is the right option. Now for a channel section subjected to a downward vertical shear force at its centroid, which one of the following represents the correct distribution of shear stress in the flange and web? So in case of channel section, my shear center will be here. My shear center will be somewhere here. What does it mean? When shear force act at this point, then no twisting will be there. So shear flow in this case of channel, it will be like this. It will be 0 here. Similarly, and for this section, it will be like this. So in this case, this C is the right option. Which one of the following stress condition represent the state of pure shear stress case? So these are three options. For this case, for pure shear, in case of pure shear, my normal stresses should be equal to 0. If I draw a more circle for this portion, then it will be like this. This is the origin. This is 40 tensile. This is 40 compressive. And shear stress is, this is 40, this is 40. So obviously this is 40, this is 40, this is 40, and this is 40. So it will pass through the origin. So my more circle will be like this. So it means, so it will the more circle. For this case, it will be like this. This is compressive 40. This is also compressive 40, and this is 40. This is also 40 positive, and this is 40 compressive, and this is 40. So its more circle will be like this. In this case, this is tensile 40. This is also tensile 40, and this is positive 40. This is negative 40. So its more circle will be this way. In this case, it is tensile 40. Shear stress is 0, and this is also tensile 40. It means my more circle will just a point here. So out of these 4 options, this one is the case of pure shear. Pure shear means so where in this case my shear stress is maximum here. This is Q max. This is Q max, and at this location my normal stress is 0. So when Q shear stress is maximum, my shear stress is 0. So this is the case of pure shear stress. So this one is the right option. So I hope you enjoyed the lectures. So thank you very much, and good night.